High-level programming hides the complexity of memory management, but the execution of modern Java relies on a specific mechanical architecture within the JVM. Many developers view the features introduced between Java 11 and 21 as shorthand intended only to reduce boilerplate and visual clutter. In reality, these enhancements modify final class structures and introduce strict compile time constraints into the generated bytecode. We will map the mechanics of var, records, and sealed classes directly to their respective JVM runtime constraints. This analysis moves below the syntax to see how these abstractions alter parallel execution limits and modify security profiles. Treating these structural modifications as cosmetic shortcuts results in a misunderstanding of how the JVM manages state and execution at scale. Parallel stream pipelines can encounter a CPU bottleneck that causes them to execute slower than a basic single-threaded loop. A splitterator cleanly divides an array. With exact index coordinates, the dataset partitions into symmetrical, balanced subsets for the fork join pool. Contrast this with a sequential source like Stream.iterate. Without index coordinates, the splitterator cannot partition work evenly, resulting in an asymmetrical, stalled workload. The stream cannot calculate the next value until the current one is produced, which forces the splitterator to estimate bounds. All parallel threads stall while waiting for the single-threaded sequence generator to yield the next integer. Adding a dot limit operation to an unsplittable sequence further compounds the performance drop. To guarantee exact order, the JVM manages heavy synchronization. This causes severe thread contention, completely blocking the shared global pool. Without understanding the partitioning mechanics of the underlying collection, a parallel stream can stall the entire application's execution environment. The var keyword does not change Java's commitment to static typing, though it is often mistaken for a move toward dynamic types. During compilation, the Java compiler analyzes the right-hand assignment and injects the definitive target type directly into the bytecode. Since this happens at compile time, there is no runtime cost, and the variable type cannot be changed later. Usage is restricted to local scopes, method body declarations, try with versus blocks, and loop indices. The compiler prohibits var for class member fields and public API method signatures. Using type inference in public boundaries would obscure the class schema, making the API difficult for other modules to interpret. The JVM limits var to local execution to preserve type safety across the broader application structure. Java records provide a streamlined way to define data carrier objects without the boilerplate code of traditional classes. A record declaration translates into a final class, where the compiler synthesizes the fields and accessors. Records only enforce shallow immutability. While the reference pointer is final, the internal state can still be mutated by external inputs. To achieve deep encapsulation, a compact constructor creates a defensive, unmodifiable copy of the data during instantiation. This structural rigidity also provides a specific advantage when handling object deserialization. Traditional serialization is vulnerable to exploits, often bypassing constructors to create objects from binary streams without validation. With records, the JVM forces deserialization through a canonical constructor gate, validating every parameter against class constraints before creation. Records function as a structural defense, ensuring that state manipulation and binary injection are checked by class invariants. Historically, Java classes were either open for extension or completely locked. There was no middle ground for restricted inheritance. Sealed classes provide control over the inheritance hierarchy. By using a permits clause, an interface can explicitly define which subclasses are allowed to implement it. Any class not listed in the clause will fail to compile if it attempts to implement the sealed interface. This closed topology integrates directly with the pattern matching engine in Java 21. When using a switch statement on a sealed hierarchy, the compiler knows every possible subtype, systematically extracting data and eliminating the need for a default block. Because the hierarchy is closed, the compiler can mathematically verify that every possible case has been handled. Sealed topologies shift the enforcement of domain boundaries from runtime checks to compile time verification. Applying these modern features in an enterprise environment requires a set of architectural constraints. The first axiom for type inference is to avoid var when it hides the semantic intent of the data layout. Favor var only when it removes redundant declarations, where the type is clearly visible in the initialization. For records, maintain object purity by using them strictly as data carriers. Operational workflows, database hooks, and heavy business logic should be kept out of record declarations. If a data object requires mutable state or complex operational overhead, a standard class layout remains the appropriate choice. Modern Java enhancements are designed to shift execution risks to the compile time phase, locking down memory visibility and enforcing application boundaries through the type system.